Okay, so for today class, we will go through a conservation of mass concept, which you already done in your previous module. So again, every system you will have a mass. So we are looking at, if you look at a time frame, means we will have a m dot or d. We take the differential of mass divided by time, and we have a if we have a conservation of mass applied to our system, means there is no change of mass for in our system. So mathematic model is dm over dt equal to 0. And then if you want to find the total mass, you just integrate the differentials difference in the mass inside the system. Okay, and if you mention about second Newton law, then it is F equal to ma.
Mm-mm.
So okay, let me mute your mic. So because if there's some background on your side. Okay. All right, so second Newton law will be F equal to ma, yeah, F equal to ma. And if you talk about momentum of the system, then we will integrate our velocity with our time, because momentum, the physics, mathematics for momentum is momentum equal to mv, mass times the velocity. So what you're seeing on the screen here is a mathematical model or mathematical formula that we already covered in your other module. And then first law of thermodynamic, or second law of thermodynamic, is all about conservation of energy. It's about energy. So we talk about heat transfer, the amount of heat and amount of work. Q is heat, W is work, and the differences between your heat energy and your work will become the change of energy inside the system. Okay, yeah. So this formula will be applied in your simulation later on. You need to explain why you get a certain energy at a certain section of the component. For example, if you get a very high number at a band of the pipe, or at the edge of the heat sink, then you need to explain why you get a certain value. Why is it the input of the heat is high, or there's a work done or less work done on the system. So you need to explain based on all this theory. And another fundamental equation is E equal to U plus V squared divided by 2 plus 3Z. This is very near to a Bernoulli equation that we covered in your year 2 or year 1 module. So this is the second thermodynamic law, which is deal with entropy. So entropy deal with the rate of change of your heat transfer into the system. And yeah, so all these are just a derivation of equation. So at the end, we will arrive at continuity equation. So it's important that for if you use a CFD or ANSYS or any software that simulate flow, make sure you understand what is continuity equation, which is in this form. So you will look at your control volume, and you'll look at what is happen to your control surface. So that's why when you use the CFD, when you set your boundary or your computational domain, the computer or the software will look at what happened at the control volume. What happened will happen at the control surface. Okay, and then there are some function that you can set inside the software. For example, in ANSYS, you can set that you are running incompressible flow. Then the software itself will set the rho as a constant in the meshing and also in the computation steps. Okay. So all these are the steps that will run by the software itself when you set incompressible scenario. So it will use this equation and then it will simplify the steps. Okay, and then you can calculate the Q, the volume flow rate through the computational domain. Okay. If you have a steady compressible case, then the computer will cancel the first term in the equation. So you will set the first term equal to 0. Then you will run the calculation for the second term. Which is you will focus on the control surface. All right, so let's look at one example where you will see in your handouts. Your handout, I think this one is in your tutorial chapter 3, document name 3b. This one will be under tutorial question number 28. 28. So we have a system. So maybe your coming test or in your coming assignment, you will face the similar scenario where I give you a photo, a picture, then you need to draw the model using the modeler, and you simulate the domain, simulate the scenario. So given a joint pipe, as you see on the screen here, so you have one inlet and let me see here. So okay, the question mentioned we have a steady flow in the water pipe, and the area is given. Area 1, 2, 3 is given, and in additional, the fluid is lost out of a hole at number 4. So there's a leak at position number 4. Estimated at a rate of so and so. So the leak, the fluid flow out from point number 4 is given. Average speed in section 1 and 3 is given, and find the velocity at section 2. Okay, so you will have one inlet, 2 outlet, 3 outlets. So inlet number 1 is your input, and then 2, 3, 4 is the outlet. So number 4 is a leak, number 3 is a normal outlet, and want to find the velocity at point number 2. So in the simulation later on, you need to build the pipe of this joint according to the spec given. So you estimate you spend around like 30 minutes to build the model, and then the rest is just setting on the boundary condition, and then do a proper setting in the ANSYS itself. Then you run according to the correct model, and then you find the velocity at point number 2. Okay, so these are the information we get from the question itself. We have the steady flow, and then we have the area of number 1, number 2, and number 3, and we have a velocity at point 1, point 3, and the density is given. So in this case, we have water. So in ANSYS, you need to set the material to water when you simulate. All right. So this one will be quite similar to the example that I gave you in the previous lecture for the ANSYS workbench exercise. So the workflow at number 4 is given. Okay. So you need to set a domain for number 4 at a certain value. So velocity number 2, you need to find. Okay, then the step will be the same as what you did in the simulation. So you choose a control volume, which is you set your domain, your simulation domain, and then you go through the setting according to the assumption. So then you label the diagram accordingly. So in the ANSYS, you will label, or you will go for the step, we call it selected section, or name selected section. So you will name the surfaces or the volume accordingly, and then you do the other setting. So in the process, if in this case we assume that we have a steady state, so there's a setting to set that is a steady flow, and then we run for incompressible flow, and then normally in this case we will use the turbulent K epsilon or K omega model to run for the turbulent flow in the pipe. Yeah, so governing equation is what we covered just now. So we consider what happened to the control volume and control surface. So if we have a steady flow, what happened to the control volume? Pratibha, what happened to the control volume if you have a steady flow? What happened to this term?
Control volume is constant, sir.
Yeah, constant. So what is the value? Yeah, it's a constant, but when you differentiate with time, so what is the value? When you differentiate a constant value, what value you get? What value you get? When you a constant value, let's say I give you 100 over dt. What value you get?
100t, sir.
100d? When you differentiate a constant value, 100?
0, 0, 0.
Okay. You need to polish up your mathematics. Okay. When you differentiate a constant value, you get 0. Okay. Then you focus on what happened to the control surface. Okay. Then you work on the control surface. So this is domain that you will set in the ANSYS later on. And you look at point 1. Point 1 is you take the velocity times the area. Point 1, dot products. And then point number 2, you take velocity at this point times the area. Number 3 also same, and Q4 is given. So you don't need to find anymore because the value is given. So velocity times area, you get the Q, you get the mass flow rate. So you need to be careful when you transfer the value inside the calculation. So when we calculate the vector form, you look at section number 1, you take V1 dot your area here. So our area will always pointing out. In this case, our area is pointing to the left corner, and our velocity is going in. So if these two is not same direction, you will get a negative products for under the dot products results. So if these two vector have a different direction, then you get a negative result. So the first one, the vector 1 times the vector 1 for the area, you will get negative velocity 1 times the area 1. So this is the concept when you use on the control surfaces. So number 2, if you have vector 2 and area 2, so you see number 2 here, how we draw all these vector, you start with the area first. So if the area number 2 is open, so it is pointing downwards, meaning it pointing out. and then your velocity is going out from this point. So your v2 vector number 2 is going out. So since you're seeing the same direction, then the product will be positive. Okay, so v2 vector dot a2 vector equal to positive products of the velocity at point number 2 times the area of section number 2. Then we look at section number 3. Again, you draw section number 3 and then you go for the area. Go for the area. You draw the area direction first because the outlet number 3 is pointing out, and then the velocity is going up also. So if you times these two vectors together, or when you see the arrow is going together, then it becomes a positive entity. So it's quite straightforward. Like the principle is still same like what we did for point 1 and point 2. Okay. So after that, we put in all the value inside this equation, and then we substitute all the value that we know. So from here, we're able to calculate what is our V2. So V2 equal to V1 A1 minus V3 A3 minus Q4 divided by A2. Okay, the velocity is V2 equal to negative 4.5 meter per second. All right. So later on, what might be happen in your test will be, for example, I ask you the value at number 2 after your simulation. You from the simulation itself, let's say you get a color of in the legend of the ANSYS, you'll see there's a velocity chart here, and then you can check what is the velocity at point number 2. You can ask the software to pinpoint the location. So the location of simulation, let's say you get the location for this one, maybe the velocity in the software, you get 4.8 meter per second. Okay, so you need to explain how you arrive at 4.8 meter per second, meaning what we expect from your answer will be what concept you use, what assumption you use, what equation you use. Okay. All right. So you need to explain how you arrive at this answer. Okay, not only how to click here, click there, or how you use the software. Okay, we want to test whether you understand the background of the simulation. Okay, all right. So in this case, so in this case we get a negative. Negative means the velocity is going in at point number 2. So you have an inflow from number 2, means number 2 is not the outlet. It's not an outlet, but it is the inlet. Or it's not inlet, but you claim that the flow is, you have a backflow at point number 2. So you need to argue the point, meaning from the ANSYS itself, you're able to see the legend. You have a positive value and negative value of your velocity. So maybe you are seeing a negative value over here. You will see if you run for vector form, you will see some arrow pointing this way. So you need to explain what happened to point number 2 with all the input. Okay, what happened to point number 2, you need to explain. Okay.
Sir, the why? Okay, sir. Sir
Mm.
say the inlet is negative.
No,
Then
before we start, we assume that this is inlet, this is outlet, this is outlet before we start analysis. So that's why in the beginning, we draw all these solid arrow. Understand? And then we run the governing equation. We run the control surface equation. And then after our analysis, we get negative. In this case, we get V2 equal negative 4.5 over this point. So what mean by negative? It means that the arrow that we assume in our analysis is incorrect, or it do not agree with our calculation. So the real case is that we will have a inverted velocity go inside the pipe with a magnitude of 4.5 meter per second. Do you understand?
okay, sir.
So this is that's why sometimes in a simulation, you will see some backflow, or you will see some the arrow. In simulation, if you open up the vector illustration as your results, right? So you will see all the arrow showing in this one, and then suddenly you will see some arrow at this one. You will see some arrow, and then the color, of course, will be different now. So I just throw out what is expected in a simulation. So if you have the same system like what you see on the screen here, you do the proper setup, you will see some arrow that going in rather than going out. So of course, you when in the simulation, you can name point 1 is your inlet, point 2 is your outlet. But when after you get your results, you look at the result and then you say that there is a backflow at point number 2, or there's a backflow at your outlet. Okay. Maybe you go for one more example, and then we stop our lecture for today. Okay. This example is about boundary condition or boundary layer, which you can find in your tutorial question number 29. So this is also one of the fundamental equation used in any CAD software simulation, especially when it comes to fluid. So this question is more about the boundary layer, and we know that this boundary layer will define whether the flow is laminar flow or turbulent flow. Okay, yeah. So the question gives us some information. So let's say we have a fluid that have a direct contact with a stationary solid boundary, have a zero velocity, which is here, zero velocity. You know that all the fluid that contact with the surface, we have zero velocity. There's no slip at the boundary, and the flow over a flat plate adverse to the plate surface and form a boundary layer. So this is what we already observed in our derivation for the boundary layer, what we learned in our fundamentals of fluid mechanics. The flow ahead of the plate is uniform. So before the flow contact with the plate is uniform flow, given by this vector v equal to ui. So the magnitude of your velocity is 30 meter per second. So again, in ANSYS, you also can set your direction and also the magnitude of the velocity. The velocity distribution within boundary layer is given so and so along CD, which is this one. So it means the boundary layer thickness, or the ratio of your u divided by u is given in this equation. The boundary layer thickness located at D, which is here, is 5 mm. So you know that the boundary layer after a certain distance, A to D, the boundary layer thickness at location D will be 5 mm. The density is given, so of course in ANSYS you need to check whether you use the correct medium or correct material. So you need to set correctly. Or the fluid is air. Okay, we're having an air here. So yeah, previous example is water, so this one is air. So in ANSYS, by default is air. Okay, by default is air. You need to do some setting if you use water. Assume the plate with perpendicular water to be 0.6, so W is given. You need to calculate the mass flow rate across the surface of BC. So you need to calculate how many, what is the value of m dot that flow across this line, this dotted line, BC. Okay. And we have our control volume of ABCD. All right. Now, the question gives us some information. We already mentioned steady, incompressible, and we have air. The medium is air. Velocity, magnitude also given, and the direction is along x-axis because it's given us a I unit vector, which means our velocity is along x-axis. Okay. And the thickness of the boundary layer at position D to C is 5 mm. When you use ANSYS, remember to check the unit that you use before you run any simulation. There's a setting that you need to set. Make sure the unit you set correctly. So normally we'll use mm in our simulation for accuracy, and you can check the unit in your project window in ANSYS. So let's say you have a object inside the project window here. There's a ruler bar below here in the ANSYS. So you will see whether it's right meter or mm below here. There's a black color, white color ruler here. Okay, so make sure you set the correct dimension when you run any simulation. And for the model also, the model also use mm. Yeah? So when you import or you do modeling using the modeler in the ANSYS especially, make sure you use the correct unit also. Okay. So the next is just look at the equation that we're going to use. So we're going to use the continuity equation or that derived from the equation of mass, right? Conservation of mass. So again, conservation of mass, especially when it comes to continuity equation, we look at two domains. One is the control volume, another one is the control surface. So assumption, we have a steady flow, incompressible, and we're going to look at 2D condition, 2D flow. Okay, so when it comes to exam or test, let's see if you will have a 2D or 3D scenario. So I'll brief you more when it comes to your test. So again, if you have a steady flow, if you differentiate something with a constant value, then you get a 0 for the first term in the equation. Right, then we focus on what happened to the control surface. So control surface is very sensitive to the vector dot products, like what we've seen so far. And because this is a 2D analysis, so we don't have flow in the Z direction. When we look at a control surface domain, meaning we look at all the surfaces we have. So in this case, we have 4 surfaces here. We have AB, BC, CD, and DA. So we have 4 surfaces, and we know that there's no mass flowing across AD. Yeah, there's no mass across this one. There's a plate at the bottom. So when you calculate the mass flow, go into AB. So you focus on AB, and then BC, CD, and so on. So again, we know that there's no flow at the bottom, so we can straight away cancel the last one. Okay. And of course, in the ANSYS, when you set the boundary layer and you set that there's a contact at a certain surface, then it will automatically calculate for you. Of course, in the simulation, you will see there will be some flow value or magnitude just above the surface. But along the surface, the contact, then you will get 0 value along the surface if you set the no slip condition in the simulation. Okay, then yeah, the rest is just calculation from there. So the mass across the BC here will be integration of your rho times the velocity vector dot dA. It will be BC will be the negative because you move the equation to the right. We focus on this term, the second term, 1, 2, 3, 4. We have 4 terms earlier. You remain the second term on the left. Then you move all the equation, these two, AB equation and CD equation to the right. Then you get negative, and you analyze each portion. So we start with the BC. Maybe we start with the AB first. Yeah. So what happened to AB is that you need to draw the vector arrow first. So again, area, we start with the area. So area is pointing to the left, and the velocity is going to the right. So by looking at the vector diagram on the screen here, you know that the products will be negative. Yeah, will be negative. And then the rest is just mathematics derivation expansion. So you get negative for if you analyze surface AB, then you'll get a negative integration of rho u dA. You change the velocity of v into u because it's in the x direction, and then you further expand the dA. How you calculate the area? You take the w times the y dy. It is here, right? It takes the w, the width of the plate, times or the width of your domain times the height of your domain. Okay, then you integrate from A to B. So in this case, we know that the height, the location, if you look at a rectangular coordinate, so A is 0, and we're given a thickness of our domain. The thickness of our domain will be delta, which in this case is 5 mm. So you put inside the equation 0 to delta, then you run the calculation. Okay, the rest is just from integration steps. Okay, so at the end you get negative rho uw delta from the calculation steps. Okay, so we have done for the first one. We will do the same for the another side. It is CD. Okay, so again, if you analyze CD, you draw the vector free diagram first. You look at the area first. So area is pointing out always. And the velocity, in this case, you look at the scenario. So in this case, the velocity is going to the right. So you look at the combination of the two vector inside the diagram. If these two go in the same direction, then you will get a positive products. So in this case, so rho v dot dA, we can write rho u, substitute your v vector with the u dA, and then you substitute the boundary condition for CD. So CD, you take integrate from D to C. Again, we are seeing the delta, the thickness of the boundary layer here. So we integrate from 0 to delta, and then you follow up with the mathematics calculation, right? In this case, you substitute the boundary layer equation which is given in the question, because just now you mentioned that at this point you having a velocity distribution given by u divided by u equal to 2y divided by delta minus y over delta divided by power 2. We just substitute inside there, and then you do the calculation. Yeah? So at the end, for mass flow that go across boundary, go across the line of CD, will be 2 rho u w delta divided by 3, and then you combine the two equations. Yeah? I think there's okay. So you combine what you get so far. So mass flow across BC will be negative negative rho u w delta minus, because just now in the earlier our equation is negative, so negative 2 rho u w delta divided by 3. At the end you arrive at rho u w delta divided by 3. So you substitute all the value given. If you do the hands-on calculation, remember to change all into unit SI. However, in the ANSYS itself, just be careful to set the correct unit in the simulation. So, and then at the end, your answer will be around 0.03 kilogram over second. So this is, you will see, you can also check in the simulation at this point or certain point or along this plate, what is the m dot that go across this point. So there's a value that you can check. Okay, so this exercise also covered in the second example that I covered for the parametric setting in the ANSYS. So the last few steps when it comes to results, when you key in to get a certain boundary layer, you can get the value over that particular surface or section or domain. So in ANSYS, you can pinpoint a certain location and look at the value that appeared at that particular time and location. Okay, so this is how we analyze, and in by hand calculation, we know that m dot across BC is a positive, so mean that the flow is flowing out from this domain, which is agree with the normal behavior of the flow, because if you can see here, the flow is flow from the left to right, so the flow will somehow will go up a little bit and then continue with the journey to the right. So the flow will go out, So that's why you get a positive in this case. So our analysis seems logic and makes sense, right? So in simulation, you'll see, again, you can set the vector arrow here to see the flow. above the plate. Okay, I think stop it here.